Tak já vás vítám na první přednášce tento semestr výzkumné skupiny Go.
Že jsou tady lidi, co nemějí česky.
Let me welcome you on the first lecture of our Go research group. The first lecture is by Pavel Dvořák on sliding window algorithms for weighted matching.
Okay, thanks. So, sliding window algorithms are some kind of a streaming algorithm. So, who knows something about streaming algorithms? Like what it? Okay, yeah. So, in this type of algorithms, you don't get an input as a whole at the beginning, but as a stream of some elements. So, we are interested in matching. So the stream is a stream of edges. So we get some stream of edges at as input, and at the end of the stream, you need to compute some output. In our case, when the stream ends in some edge ek, let's say, then at the end we want to output matching in the graph spanned by these edges. So that's easy, right? We just store the edges and then compute the matching. So yeah, end of story. You can go home. But the problem is we try to limit the memory as much as possible. So we want to compute the matching, but use only memory. Let's say O tilde n, where this tilde hides the polylogarithmic factor. And so this is somehow holy grail of it, that we use only, let's say, linear memory. If we cannot design this algorithm, then as small memory as possible. So this is like a standard streaming model, and probably you can see that, for example, to compute two approximation for matching, we just store the maximal matching in the graph. So just example, first edge count, we store this. Then if another edge count, if it's incident with some our stored edge, we just delete it and don't remember it. Another edge come. So in our memory, there are only blue edges. So we can add this edge to our matching. Then maybe this edge come, we delete it, and so on. So at the end, we have a maximal matching in our memory, and this is it's known that it's easy to see that it's a two approximation of a maximum matching. So so this is somehow standard streaming model, and we study so-called sliding window model. So there is another thing. There is like this stream of edges, and there is a sliding window, and with some fixed length. So there is a known parameter L, which is a size of the sliding window. And so in the standard model, we need to output the matching at the end of the stream. In the sliding window model, when new edge comes, we need to output matching spanned of graph spanned by last L edges. So again, we have some stream of edges. some edge come, we looked on L last edges, output a matching mi. The next edge come, we slightly shift our window by one, output another matching or approximation of the matching, and so on. So is this a sliding window model clear? So
I have a question about the memory you are mentioning. Do you mean the memory like the size of the solution that you want to output, or also
no, all memory you use?
All memory.
All memory, yes.
Thank you.
So here somehow L is somehow super linear in N to be the problem somehow interesting. So any other question about the model? Okay, so also one remark, like I will talk about weighted matching. So we somehow suppose that the weights are somehow nice, that like the encoding of the weights are small, like you can encode it in log n bits and so on, that like our algorithms are more like a combinatorial algorithm than we didn't anything about like optimizing the weights encoding or some like bit operation on or whatever. So always weights are a nice number. Okay, so maybe what are known about the sliding window algorithm? So for matching, there is a 3 plus epsilon approximation, and the used memory is like almost linear. This epsilon is somehow hidden in this O notation as well. Usually it depends like as the memory depends polynomially in 1 over epsilon usually. And then weighted matching. So there was some 2.0 to 7 approximation in the same memory. These two results are from the same paper. Then it was improved to 6 plus epsilon memory and 3.5 plus epsilon memory approximation, sorry, in the same memory. And then we close the gap between weighted and unweighted matching. That so we provided 3 plus epsilon approximation in. So this is our result. And then we have also the 2 approximation, but in with the worse memory bound, and it's a square root of n times L. When L is at most let's say n squared, so this is at most like n to 3/2. So it's still better than I remember all edges. Okay, so first I try to present this algorithm for unweighted matching, and then discuss how to use it for weighted. Any question? Okay, so first idea, how to design two approximation for sliding window. So we have this stream of edges right here, and if we can somehow compute the maximal matching of that stream, but in reverse order, then this is like very nice to use for the sliding window, right? Because we have this stream of edges, and if we have maximal matching, meaning greedy matching in that order. So if we have some matching m hat, which is a greedy matching in the reverse order, then when we shift our this is our window of length L, and when we shift it by new edge, then we can just delete this if the deleted edge from the previous sliding window is in our greedy matching, then we just delete it and possibly add this edge. So it very nice behaves with this shifting of this sliding window. The disadvantage of this, to compute actually the greedy matching in the reverse order, you need to remember all the edges. But this was somehow the first idea, and now what we can do is that we split the stream in a block and only compute the greedy matching in reverse order in the last block, and then add the greedy matching in the right order. And when we compute it, then it gets to this algorithm. So now a little bit more formal. So this is somehow all stream, and we divide a stream in block of size S, where we determine as later, and somehow the picture for this algorithm is in the second page of your handout, and now we always remember all edges of the last block. So now the edges of these blocks are arriving, and when we are at the end of the block, we start to compute the matching in the greedy matching in the reverse order. So and so we are adding edges and computing the greedy matching, and when so this is a matching, let's say M1, and when we stop, So when we create a somehow arithmetic progression of this matching. So we have here matching M2, here matching M3. All these are really matching, and what's the property of this is that size of matching M2 is larger than 1 plus epsilon of matching M1. And this holds for all matchings in this block. So in general, the next matching is always 1 plus epsilon larger than the matching before. So and then so is this somehow clear? What are the thing is we compute only logarithmically many those matching because their size is like is increased with some 1 plus epsilon factor. And so from this block we have several of greedy matching. So we have matching M1, M2, M3, and so on. And then so this is processing of the first block, and then we remember only the edges of this matching and delete all our all other edges from the first block, and then we start to process the next block. We again store all the all edges from that block, plus we are increasing this matching in our memory. So if somehow new edge E come in our next block, then we add it to all of these matching we can. If it meaning if M1 plus E is still matching, then we replace M1 with M1 union E. If M2 is not a matching with E, then we don't add E to M2. And again, so so if we have let's say this is the next block is a stream T, so then the matching M1 is a greedy matching of edges. So let's call this stream F1. So when we are in this position, then M1 is a greedy matching of stream F1 processing backwards and T processing forward, and so on. And again, when we are at the end of the second block, we do the same process with this stream that we create new instances for the next block and delete all edges that are not used in this instance. So so how much space is used? So and of course, if some block is completely outside the sliding window, we delete all instances before. So how many blocks we have? So number of blocks is L over S. How many instances we store in for each block? So each block each block has at most 1 over epsilon log n instances. Why? Because the size of the instances grows with arithmetic progression, geometric, and each instance store at most n half edges, because each matching can have at most n half edges, and we store only the matching. So for the stored instances, we have the memory for these instances is at most L over S times n half times 1 over epsilon log n, and we store all of the edges of the last block. So plus S, which is all edges of the last block. And now, if we set S to be this, so now we set S to be the square root of n times L. When we can ignore this term, this is somehow not interesting for us. Then we get bound for the memory L over S times n plus S, and when we plug this value for S, it's what I promised. So this is a memory bound, and now why it is a true approximation. So suppose the sliding window is somewhere here. So in this case, we output the matching we store in M1, because if we output the matching in M2, it may contain an edge which is not in the sliding windows. It would be an invalid output. But maybe we lost some edges, but because the matching in M1 and M2 are not so different, then we don't lose like many edges. It's only like a epsilon factor of loss. So when should I end? So how much time I have?
10 minutes.
10 minutes. Okay. So what do you want to hear? I can provide you a little bit more formal analysis of this, or somehow talk more about weighted matching and the other result also. So who want the weighted matching? Okay. Who want a more formal analysis of the approximation factor? No. The analysis is not hard. Like it's quite straightforward. So okay. So more about weighted matching. So there is a two approximation streaming algorithm, not sliding window, but streaming algorithm for weighted matching from Pass and Schwarzman. and it should be also in your handouts. It's algorithm 1, and it works like this. So PS algorithm. So it's standard streaming algorithm. Oh shit. So new edge. So we have some stack which you use in the processing of the streaming, and then new edge array. Let's say between vertices U and V, and W is so if weight of the new edge is smaller than 1 plus epsilon times phi u plus phi v, where this phi is some potential of the vertices which you compute during the processing. So it means that the weight of the edge is somehow small, then you just ignore the edge and set something called reduced weight of this edge to be 0. And if the edge is somehow large, then we set the reduced weight of this edge to be the difference of its actual weight minus the potential of the vertices, and then we increase the potential of the vertices by its the reduced weight of the edge. And we put the edge into the stack. And so this is the processing of the stream, and at the end of the stream we output greedy matching of the stack. So somehow the greedy matching here is also in reverse order. And so this is a 2 plus epsilon approximation. Interesting thing is somehow this at the end of the stream, this potential of the vertices is almost somehow up to 1 plus epsilon factor weighted vertex cover of the graph. So it's like a dual solution for the matching. And they prove that this is actually a 2 plus epsilon approximation. And somehow how we transform this algorithm for unweighted matching to weighted matching in the sliding window is that we use this algorithm. Here we use a greedy matching algorithm. So we replace this algorithm with a Pass and Schwarzman algorithm. But here it's important we don't compare the size of the weight of the outputted matching. We compare the sum of reduced weights. So So here we use Paschen-Schwarzman algorithm, and instead of size of the matching, we use sum of the reduced weight, but not in the output matching, but in a so when Fi is the stream where we computed the matching Mi. So you can see here that even some edges that are at the end not in the computed matching, they can have non-zero reduced weight. And so we sum all we sum reduced weights of all edges of the stream and use it to as our indicator where to start the new instance. And so somehow, what does it mean? Somehow the reduced weights here, in some sense, has same behavior as a greedy matching in unweighted case, and that's also the case how we improve this this result from 3.5 to 3, because how these results are done, we basically compute the matching, and when the matching started, it's a similar idea as here. When the matching started to be very different, we start a new instance. And the previous result was that they compare their instances based on the output of this algorithm, and somehow they get the 3.5 approximation. We have example that if you use the output of this algorithm, then you cannot do better. Like that was this 0.5, this 1/2 was not because they did like sloppy computing. There are actually instances where their algorithm achieved this this approximation factor. But again, if you compare your instances not based on the output of this algorithm, but based on the sum of the reduced weights, you can remove this 1/2 and get a 3 approximation. And as you can guess, probably this algorithm and this algorithm are the same. Here is the algorithm for greedy matching. Here we use again this Paschen-Schwarzman algorithm with comparing the instances on reduced weights. So, like, take-home message: if you have like something which works in the streaming setting, something which works for greedy matching in an unweighted case, and you want to transform it to like weighted matching algorithm, use Paschen-Schwarzman and try to use reduced weights from it. Okay, I think I'm basically on.
Any questions?
Is it somehow obvious that there will be too many edges in this Paschen-Schwarzman?
How many edges are?
Yeah.
Yeah. Why did this? Yeah, it's a so. In the first version of this algorithm, there is at most like n log n edges, because if you store an edge, like it's because of this, right? Somehow the weights is in some sense significantly larger than the previous edges. So yeah, so here if you have a vertex, then its incident somehow to at most logarithmically many edges that are stored in stack because of this. Then there was an improvement of this algorithm, and they proved that actually with you can store at most constantly many edges per vertex, because the first edges somehow that are incident to that vertex as so small weights, then you can store at most some constant of many edges to incident to each vertex. So they improve it that you actually can store only linearly many edges in this algorithm.
So you mentioned a model where you consider matching in the graph spanned by the last L edges, but is there also some model, or is it even interesting to study that I want to output the matching of the first, like from the ith edge, I output a matching from the first I edges. Like, I would not move the left point of the sliding window. Is it somehow interesting, or?
It's streaming, right?
Yes. At every edge, I would have to output the matching.
Yeah, in streaming you can
just recompute something.
Like yeah, if you have streaming algorithm, then you can output like the new matching with each new edge, right? You can consider it like the end of the stream. You can output your matching, right? And then somehow pretend that your stream like don't add a new edge. So yeah, so this is somehow so this is only like an insertion model that you only add edges. Like the most general model is that you can also delete the edges, but it's far more complicated. This is somehow you can model this sliding window as like a insertion deletion model, but the deletion are very somehow structured, right? You always insert an edge and delete the last edge or
is this approximation factor for this memory optimal?
Good question. So there is, so far as I know, there is one lower bound for streaming algorithm. We don't know any lower bound for sliding window, and it's a theorem 2 in your handout, and so there is a gap between upper bound and lower bound. So the lower bound said that there is a no streaming algorithm for matching with approximation factor 1 plus natural logarithm of 2 with memory smaller than n 1 plus 1 over log n. So just to explain these things. So this number is something like 1.69, and this memory is bigger than this is much bigger than n times polylog n. So if you want this memory, your approximation factor is bigger than this, but still there is a gap between this and 2. So, and
And that's for
Streaming.
streaming.
Yeah, this is a general streaming. This is not sliding window. We don't know any lower bounds for sliding window algorithm.
Are there any other questions? Then let's take a speaker again.